Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is p block elements. In p block elements, the last electron enters the outermost p subshell, outermost p orbital. So these are called p block elements. As there are 3 p orbitals, so in each orbital we can place 2 electrons, so a maximum of 6 electrons can be accommodated, and so there are 6 groups of p block elements starting from group number 13 till 18. Group number 13, the first element is boron. For 14 group, the first element is carbon. For 15, it is nitrogen. For 16, it is oxygen. For group 17, it is fluorine. And for group 18, the first element is helium. And the next element corresponding to second period is neon. The general electronic configuration of p block elements is ns2 np1 to 6. So first group of p block elements, group 13, will be having the configuration ns2 np1. This will have ns2 np2 and so on. The inner core of these elements may, however, differ. So the difference in inner core of the elements greatly influence their physical properties such as atomic and ionic radii, ionization, enthalpy, etc. So even though the outermost configuration will be same in all the elements of a group, the inner core may vary, and because of which their physical properties may also change. Consequently, a lot of variation in properties of elements in a group of p block elements is observed. Now, the maximum oxidation state shown by a p block element will be equal to the sum of the s and p electron, the total number of valence electrons. So, the number of possible oxidation state increase towards the right of periodic table. In addition to this group oxidation state, p block elements may show oxidation state which normally but not necessarily differ from the total number of valence electrons by unit of 2. So important oxidation states exhibited by p block elements are, let us take them one by one. So groups are varying from 13 to 18, integration ns2 np1 to ns2 np6. The first member of group 13 is boron, 14 is carbon, 15 is nitrogen, 16 oxygen, 17 is fluorine, and 18 is helium. The group oxidation state for 13 will be 2 plus 1, 3. For group 14 is 2 plus 2, 4. For group 15, it is 5. For group 16, it's 6. For group 17, it's 7. And for group 18, it is 2 plus 6, 8. So we can see that as we move to the right, the group oxidation state increases. They also show other oxidation states which are 2 units less than the group oxidation state. For example, the group 13 can show oxidation state of 1. Group 14 can show plus 2 oxidation state also along with minus 4. Then group 15 can show plus 3 and minus 3. Group 16 along with plus 6 can show plus 4, plus 2 and minus 2. Group 17 can show plus 5, plus 3, minus 1 and plus 1 in addition to plus 7. And group 18 or noble gases may show plus 6, plus 4, plus 2 in addition to plus 8. The most stable oxidation state of lighter elements of these groups is generally, especially for boron, carbon and nitrogen family, is their group oxidation states. But for heavier elements, the most stable oxidation state will be 2 units less than the group oxidation state. In boron, carbon and nitrogen families, group oxidation state is most stable state for lighter elements in the group. However, the oxidation state 2 unit less than the group oxidation state becomes progressively more stable for heavier elements in each group. The occurrence of oxidation state 2 units less than the group oxidation state is sometimes attributed to inert pair effect. The inert pair effect is the effect when the ns2 electrons of the heavier elements fail to participate in bond formation. They become inert. This effect is called inert pair effect. The relative stabilities of these two oxidation states, that is the group oxidation state and 2 units less than the group oxidation state, may vary from group to group. The peculiar property of p-block elements is that non-metals and metalloids are present only in the p-block of the periodic table. The non-metal character of the elements will decrease down the group. In fact, the heaviest element is most metallic in nature. As we go down, the non-metallic character decreases. Heaviest element is most metallic in nature. This change from non-metallic to metallic character brings diversity in the chemistry of these elements depending on the group to which they belong. In general, non-metals have higher electronegativity and ionization enthalpy than metals. And in contrast to metals which form cations, the elements of p-block elements or the non-metals, they readily form anions. The compounds formed by highly reactive nonmetals with highly reactive metals are generally ionic because of the difference in their electronegativity. For example, a compound formed between this metal and this nonmetal will be ionic in nature. On the other hand, the compound formed between two nonmetals is covalent in nature. So compounds between two nonmetals themselves are largely covalent in character because of small difference in their electronegativity. The change of non-metallic to metallic character can be seen from the nature of their oxides also. The oxides of nonmetals are generally acidic or neutral, whereas the oxides of metals are basic in nature. The first member of the P block differs from the remaining members of their corresponding group in two major respects. For example, group 13, the first member is boron. It differs from the rest of the elements of this group: aluminium, gallium, indium, thallium. It differs from the rest of the members of this group in terms of size and size-based properties, and also on the effect of d orbitals on the valence shell of heavier elements, because the rest of the members present have d electrons or orbitals, so the presence of d orbitals puts an effect on their properties, and as a result the properties of first member are different from these members. Boron, the member of second period of the periodic table, is restricted to a maximum covalence of 4 only, which involves 1 2s and 3 2p orbitals, whereas other members, they can show a covalence greater than 4. In contrast, the third period element aluminium of this family can expand their covalence above 4. For example, AlF6 negative is showing a covalence of 6. So this is because of presence of d orbitals. The presence of d orbital will influence the chemistry of heavier elements in a number of other ways as well. The combined effect in size and availability of d orbitals considerably influences the ability of these elements to form pi bonds. The first member of a group differ from the heavier members in ability to form p-pi multiple bonds to itself and to other elements. For example, carbon forms pi bonds with carbon. It can form triple bond also. Similarly, nitrogen can form multiple bonds with nitrogen. Carbon can also form multiple bonds with oxygen, nitrogen, with other members of the second period. So this type of pi bonding is not particularly strong for heavier p elements. There, the bonds, pi bonds which are formed are either p pi d pi or d pi d pi, which are not as stable. They contribute less to because their energy is higher, the d orbital energy is higher, they contribute less to the overall stability of the molecule than does the p-pi bonding in these smaller elements, second row elements. However, the coordination number species of heavier element may be higher than that of the first element in the same oxidation state. For example, both nitrogen and phosphorus form oxoanions, and in their oxidation state +5, nitrogen is forming 3 coordination bonds with the pi bond involving 1 p orbital. On the other hand, phosphate with oxidation state number 5, phosphorus has forming 4 coordinations involving sp and d orbitals contributing to the pi bond. So in this unit, we will study the chemistry of group 13 and 14 elements of periodic table, and the rest of the groups we will take up in next class, in the +2 class. For the time being, it's all in today's video. If you like the video, please do share and subscribe, and thank you. Have a nice day.